You're muted right now.
Yeah. Okay, let's get started. Is there anything to discuss organizationally, or you can just jump in? Let's just jump in. So, I guess the last time we started to talk about function approximation. And how to use it in planning. And we came up with a bunch of possibilities. And one of the possibilities was what we call the B2 assumption or whatnot, which was something like for every policy pi in our MDP, we are lucky enough so that the action value function of all the policies lie in this linear space spanned by our features. So here phi is this feature matrix. Which is this S by D matrix. And then phi was this feature map. Oh, these are actions. There are actions too. Okay, so these are somehow all the actions as well listed. So first action to the eighth action. So this feature extraction assigns to every state action value a feature vector. And the assumption is going to be that no matter how you choose a policy, you're lucky such that the action value function of the policy lies in the span, which means that there exists some parameter vector, the dimensional parameter vector such that Q of pi is equals to phi of theta, which is the same as for every state action pair. If you look at what is the value that you get with the features, with this parameter setting, well, it's the same as the value that you get from the action value function. And the question was, are we going to be able to use this to get query plus runtime independent of the size of the state space? When you have a generative model. Because of the nature of these assumptions that we made, we figured that maybe policy iteration is going to be a suitable algorithm. So let's see what policy iteration does. So it starts with an arbitrary memorized policy pi naught, and then for every value of k from 0 to and so on and so forth, the next policy is greedy with respect to the action value function of the previous policy. Which is policy iteration. And the reason this is hopeless, well, sorry, this is hopeful, is because because of our assumption B2, this action value function of the case policy can be represented compactly with just k parameters. So we try to reduce the computation, the whole computation that you do in policy iteration, just to computing these parameter vectors. And these have d entries in them, and that can be much smaller than the number of states. So if we can do this, then we're going to win. And we started to talk about linear regression, how we could do, how we could perform linear regression to accomplish this. Because this equation here just looks like linear equation. It's a linear equation. It's like a linear regression. If we can measure the action value function on the left-hand side up to some accuracy, then we expect that maybe we're gonna be able to extract from not too many measurements, hopefully just as many, like somehow polynomial in D and the other relevant quantities, with sufficient accuracy so that when we extrapolate using the parameter vector and the features to any other state action pair, to any state action pair, then the errors are going to be tightly controlled. So for good reasons, we actually want to control. So the important thing is that we want to control here the L infinity error. So if we come up with some theta hat of k, based on sampling, whatever computations, then we would like to see that the approximation error over the whole state action space is small. Everywhere, uniformly. If we are not able to guarantee this, then things usually don't work out. So at least we set out to try to achieve this goal, and we should check whether this is possible to achieve. And the last time we came to the Kiefer-Wolfowitz theorem, which I said is going to be a key result that is going to help us to achieve this goal. We talked about how this extrapolation error here. So I call this extrapolation because notice that this maximum norm is over all possible state action pairs. There are many, many of them, many, many more than the number of parameters that we want to estimate. And we don't want our computations or measurements scale with the number of state action pairs. We want everything to scale with the dimension and like horizon and whatever other factors which are under control. And so we're going to measure, let's say, at d values, approximately this function q. And we want to conclude from these d measurements or whatnot, or maybe d squared, or like just not polynomially many. We want to conclude that we have a good approximation everywhere. So that's extrapolation. And the last time we drew this little figure that was kind of showing that if you want to control these extrapolation errors, then maybe you should space apart the inputs, so that the feature vectors, the underlying feature vectors, somehow like nicely kind of spanning the rest of the feature vectors. And the Kiefer-Wolfowitz theorem is actually the theorem that makes this really, really precise, and for a reason that will be quite clear quite soon. So let's go on with the Kiefer-Wolfowitz theorem. So what does this theorem say? It says the following: there exists a set, which is a subset of, I'm going to introduce Z to denote the set of state action pairs, because we're just doing function approximation over a set Z, and like whether these are state action pairs or whatnot doesn't really matter. For example, for the Kiefer-Wolfowitz theorem, it absolutely doesn't matter. So there exists this set C, and there exists a map from Z to 0, 1s such that, sorry, C, if you're summing up the values of this row map for the elements of C, then you get a 1. So this is, in effect, a probability distribution on C, such that the nice thing is that C doesn't have too many elements. It has at most D times D plus 2 over 2 elements. And the second nice thing is that a quantity that we will see to be quite crucial, which is this uncertainty measure, the extrapolation error of least squares, weighted least squares, at any value in this set Z, which are the state action pairs, is not larger than square root D, where D was the dimension of the features. Okay. And here, what is this G of rho? So the G of rho is this matrix, which is called the moment matrix. So this is the matrix that is going to appear in weighted least squares when you're calculating the weighted least square solutions with the weighting of rho, and this is the matrix that you would invert. And you should think about that this is like the error blow-up factor of least squares. So of course, Kiefer-Wolfowitz knew what they were doing, so they actually wanted to answer the question, okay, if I use these squares and I want to control my extrapolation errors, is there a way to do that in such a way that is the best possible? And what is the best possible blow-up factor? And is it possible to do that regardless of the coordinate of Z over which these feature vectors are defined, such that in my least squares calculations, I only need measurements over the sets C. So there are some questions in the chat. Let's see. How do we define star matrix for a matrix again? Oh, okay, yeah, okay, all right. So good point. I take it for granted that we know what this notation is here. So if you have any vector u and a positive definite or even positive semi-definite matrix, then this u of p norm is defined as a weighted 2 norm. And it is simply U transpose PU under the square root. And you can show that this is a norm. If P is positive, definite, well, we don't actually care about whether this is a norm at this moment. Maybe later it will come up. But you need it to be a norm. So now we just know that this is a non-negative number, and that's it. Okay. So the immediate corollary of this theorem is the following. So if we indeed run these squares, so we take theta hat to be G of rho inverse. And so you recall how least squares looks like. So you're taking measurements over these sets C, and we're going to run weighted least squares where rho is going to give the weighting. And the measured values, let's say, take the form of, I don't know, some linear combination of the features with some parameter vector plus epsilon of z. Right? So this is just the least squares solution for the weighted least squares problem. That these are the values that you're measuring. So actually on, okay, so this Z prime runs over this set C. So whatever values you're measuring, you can write them in this form with some theta. So for any, so take any theta and take any epsilon which you know, assign some values to elements of Z. And you run your least squares. And if you run your least squares and then you want to know how well least squares is going to predict the measured values, where we're going to choose the theta in such a way that these epsilons are the smallest possible in our applications, right? So that's kind of the understanding that epsilon is an error. And so basically we want to say that with the least squared solution, we can predict using the features pretty well whatever prediction would come out with theta. Okay. So the result is, okay, we don't write soup in this class because we have everything is finite. So the maximum were all values of Z of the errors of predicting what the parameter vector theta would predict versus what we are going to predict with least squares is going to be at most the error that this epsilon takes, but just over C. Okay, so that's very nice. It should be times square root D. So here G of rho is as in the previous theorem, right? So rho and C and G of rho are like in this previous theorem. So here's rho, C, G of rho. Are we using these? Okay. So let's see how this works. this is quite simple. You may notice, well, there is the definition of G of rho. G of rho is the sum of the order products of the, so G of rho is the sum of the weighted order products of the feature vectors over this set C. So here there is this sum over C. There is a weighting, and this is a real number. So I could move this to the other side of this vector. Doesn't change the result. Then basically the phi would come here. That's the same thing. And then you see phi and phi transpose summed up, weighted for all values of C. So that part here, together with this feature vector, is the just G rho. So that multiplied with G rho inverse, G of rho inverse, just gives you theta. And then we have to write whatever remains, which are the errors. This is just the standard error decomposition that everyone does when they're doing calculations with least squares. So the error, the parameter error of least squares is simply the least squares run just on the errors, right? So this would be the least square solution. This underlying thing would be the least square solutions if the inputs to the least squares, the targets, would be just the errors. I just algebra. So Macron is saying something about the Kiefer-Wolfowitz theorem and strong convexity. Nothing needs to be strongly convex here. There is no convexity. Everything is finite. I don't know, Macron, maybe you can clarify what you mean, but there is absolute. So I listed all the, okay. So here I'm hiding one condition, which is that I tentatively always assume that this is finite. In fact, this is not a necessary condition for the Kiefer-Wolfowitz theorem, but it's sufficient for this theorem to hold. The only condition that you would need is that the image of this set under the feature map as a subset of RD is compact. That's the only condition that the general form of the Kiefer-Wolfowitz theorem needs. There's absolutely no convexity here. There's no Q, nothing. So I don't know. Maybe you're confusing it with something else. All right. So back to our calculations. So we want to calculate these errors. Okay. So of course I can subtract here, and I can multiply with the feature vector. So fix as z. Then phi z transpose theta minus phi z transpose theta hat. In absolute value is, do I want to write absolute value? Maybe I don't like to write absolute value. So this is just equal to this. And on the left-hand side, just going to rewrite this. by moving the matrix in. Okay, a different order. To make everything nicer, I messed up my pen. Right. So there is the error, there is the weighting, and then there is phi z transpose 0 inverse and phi z prime. Okay, so this is just an algebraic identity so far. So now I can take the absolute value of both sides and move the absolute value inside and the sum on the left-hand side, and then take the maximum of the epsilon z prime values as an upper bound on any of those values, and get that the left-hand side is smaller than equal to, okay, so just doing this, right? Putting absolute values everywhere. This is smaller than equal to pulling out these errors of the sum, and then just keeping the other things there. All right, and now recall the definition of G of rho. So this moment matrix is defined as this sum, and so it would be nice to cancel this. To cancel, and we have this G of rho here. And we have this sum over the z primes. So somehow we want to take advantage of this and then cancel out G of rho to some degree, and then just like cancel out the sum actually, and then somehow left with phi z transpose. And to do this, we notice that these weights are conveniently non-negative. They sum to 1. So we can apply Jensen's inequality. So Jensen's inequality says that if you have any function and then you have some probability measure on whatever space, discrete, and this is just a sum, and you apply, let's say you want to square this. This is the implication of Jensen's inequality. Then you can just move the squaring inside. More generally, the squaring could be replaced by any convex function. And this inequality would hold. So this is Jensen's inequality, and the specific case, a special case, when phi is the quadratic, the squaring function, which is a convex function, with that you get this inequality. So there is no squaring here, but of course we can add the square. And then if you add the square, then you have to take it away. So moving the square inside. So let's just call this epsilon approx. Approximation error. And so Jensen's inequality is going to say that just move the square inside. So once you move the square inside, you have this square there. You have a square root outside. And you may notice that this can be written as the product with itself, okay? Which we can write in this form. Phi z prime transpose 0 inverse phi z 0 inverse phi z, right? So sorry, there is a transpose there. So this is one of the terms, this is the other term. Okay. And I can drop the absolute value because these are real numbers. So nothing's going to be lost. So put back the sum. So this is equal to this. This is under the square root. And now you can notice that you can move this guy in front of the sum and move this guy after the sum, right? Because they don't depend on z prime. They can just be moved out of the sum. And what remains in the sum is this rho z prime. Okay, so you can move the matrices as well out. And then rho z prime times phi z prime times phi z prime transpose, which is what? It's the, what is that? Is it familiar? Have you seen this expression before? This sum? Yes. I've seen it. It's 0. Right? Oh, yeah. Thank you. So this is 0. So 0 cancels. That's good. It's always nice to cancel a sum. So this whole thing becomes equal. It's epsilon times phi. So 1 0 cancels. So this, I can cancel this as this guy. And then what remains is phi z transpose 0 inverse phi z, which we denoted by the shorthand, that this is just this weighted 2 norm of phi z squared. The whole thing is under the square root, lucky for us. So, as promised, this is this weighted length of the feature vector, weighted norm length of the feature vector appears indeed as the extrapolation error, right? So what this says is that if you're measuring something that can be viewed as linear with some errors, then if you look at the errors of prediction using least squares, these errors can be upper bounded by the size of the feature vector measured is in this precision matrix. This zero inverse matrix weighted norm. And the Kiefer-Wolf's theorem tells us that this is smaller than square root of d, which finishes the proof, right? Because this is what we promised, that the error, no matter how I choose z, and here I chose z in arbitrary fashion, is going to be controlled by the errors, the maximum error over z prime times square root d. That's very nice. Errors are inflated maximum by a factor of square root of d. Okay, that's good. How are we going to use this with policy iteration? So we want to do policy evaluation. Right? So we want to have this policy evaluated, find this parameter vector such that we can compute the next greedy policy in implicit form, and then continue with our process of evaluating that. That is finding the parameter vector underlying that, and so on and so forth. So the task now is going to be policy evaluation. So we have policy pi, and it has a value function q of pi. And we want to find this parameter vector, theta, such that this approximates well this policy q of pi. And I'm going to allow now some approximation error here. This is a new term, so kind of relaxing a bit B2. So, you know, maybe the policy is such that its action value function doesn't lie exactly in the span. Does it matter? Well, if the errors are small, the approximation errors are small, maybe it doesn't matter. In fact, like whatever features you choose, you can find the best theta such that these errors in the max norm are the smallest possible. And then it is going to be whatever. So Shivan was asking what is rho in the corollary. So in the corollary, it's literally we are importing C and rho and also G rho from the Kiefer-Wolf's theorem. So the Kiefer-Wolf's theorem, the essence of this is that there exists this C, there exists this rho. So that's the C and that's the rho that we're going to use from this point on. And the last time we discussed that to find these, maybe you have to look everywhere. So you can't find good design points, the set C, with similarly small cardinality, and then the rho on the top of it without looking everywhere. So we're going to allow ourselves just to look at all the features, which is kind of ugly, or you could start off with choosing really special features where these are easy to find. And the optimal design literature is full of cases where you can do this, like without enumerating all elements of SNA. But here we allow ourselves just, you know, make the task a little bit easier, just to say that, well, okay, someone is going to hand over this set C. Notice that this set didn't depend on what function you're trying to approximate. So at least if you have to do some calculation like this, you can do it once. Okay. So in other words, we ask for whoever proposes the features that they also solve this problem for us, or a similar problem. You could have a C which is larger than this, but satisfies something similar, like whatever law of vector you can guarantee for that C, the square root D could be larger. Like if it's a D, you will see that that has some implications down the line. If it's D squared, it has and so forth, right? If it's 2 to the D, then like that's really bad. Already the square root of D is like, ouch. But the Kiefer-Wolfowitz theorem actually says that, so the actual form of the theorem says that square root D is unimprovable. So it answers the question of, oh, but maybe this is a lame design. We could do much better by something better. No, the Kiefer-Wolfowitz theorem says that no matter how the feature map is chosen, you can find a C and rho such that this is achieved, and there is no better choice. So this is actually an equality there. Okay. All right, so quick question. How did I get the first line in the proof from the first line in the corollary? So basically, move this here. You have some z prime, rho z prime, phi z transpose, theta pulled out, and this sum whole thing is the same as 0 inverse G. Sorry, is 0. So it cancels. Just algebra. Okay. So back to policy evaluation. So you're gonna relax B2 a little bit. And we already discussed how we're going to do this. So you're gonna run least squares. So theta hat is going to be 0 inverse. And so same C, same rho. Z prime in C. And we're going to need to use the simulator to get some guesses at what the action values are, some estimates of what the action values are, and run least squares on these guesses. So these R hat of M at a state action pair. So Z is a state action pair. Is going to be the average return over M independent trajectories that are run using the simulator. So you start with SA, and then you run your simulator, you get a trajectory, and you do this M times. So you run these trajectories, and then along the trajectory, and the length of the trajectory is capital H. We're going to choose capital H to be large enough. And along the trajectory, you're just measuring the rewards. So the trajectory is going to be a sequence of state action pairs. And for any of these trajectories, what happens is that the very first state in the trajectory is just going to be S. The very first action is going to be A. And for any subsequent time steps, So for any t greater than or equal to 1, the next state is going to be sampled from the transition kernel of the MDP, where you are in the previous time step and this previous state of the trajectory, and this action that we have was chosen, and the actions are chosen according to this policy. And this policy could be stochastic. If you are taking greedy policies, most likely the policy that you're going to follow is going to be deterministic. So this will be very easy. But yeah, in general, you may allow stochastic policies here. It's not going to change anything. You run this trajectory. Along the trajectory, you measure the return. So this is the truncated return. You do this m times, take the average. And that is meant to be a good approximation. But it's assumed to be a good approximation, hope to be a good approximation when m is big. And lo and behold, it's going to be a good approximation. And so once you have done this, then you just run your least squares. So this is your least square solution. And now we want to see how good this least square solution is going to be in approximating Q of pi. So we want to see that Q of pi is well approximated. So Q of pi is z minus phi z transpose theta hat. And so I'm going to write this. So I want to bound this error. So then, of course, instead of Q of pi, I can write phi z transpose theta plus epsilon pi of z. Okay. And then subtract the prediction. And then now we can use the triangle inequality to get that this is smaller than or equal to phi z transpose theta minus phi z transpose theta hat plus whatever the maximum error of approximating the action wave function with the features could be if we use this parameter vector theta. Okay. And our corollary very nicely bounds this. Right. If we write this r hat of mz prime as phi z transpose theta plus whatever the remainder is. So decompose things this way. So then using the corollary, so what did the corollary say? The corollary was saying that if you run least squares on some data written in this form, so, you know, some parameter vector multiplies the features plus some error. Then whatever you get, the prediction errors of predicting whatever you plugged in here is upper bounded by the maximum errors times square root d. So now these are the epsilons. There is no pi here, so it's like that. It's the only difference. So these are the epsilons, and so the corollary says that we are interested in this guy, right? So this guy is smaller than equal to the maximum error over this set C times square root D. Okay. So clearly it satisfies if we control this epsilon z. So lo and behold, this can be controlled because this epsilon z is r hat of mz, and I see that some people already wrote in the chat that, okay, there's going to be some truncation error. Indeed, if you take the expected value of this guy, its expected value is the same as applying the Bamlon evaluation operator underlying policy pi h times to the function 0 and take its value at z. So we subtract from this its expected value. And then, well, we have to add it back. What you take away, you have to add it back. Minus, and then instead of this, well, we can just write, oops. So recall that q pi is equal to the inner product between the features and theta plus this epsilon. So q pi at z is phi z transpose theta plus epsilon pi z. So from this, we get that phi z transpose theta is equal to q pi z minus epsilon of pi z, right? So these two guys, if you compare them in absolute value, they're smaller, their difference is smaller than gamma to the power of h over 1 minus gamma. Okay, so that's the truncation error. From here, we're going to get an error which already appeared here. Let's call it epsilon pi star, so that's just a number. So that's the approximation error of the action value function, the policy. And from here, we get the sampling error. So recall that r hat of m is the average of independent random quantities. What are these quantities? These are these quantities, like there are j of them. Sorry, there are m of them. They're indexed by j, going from 1 to m. And so Hoeffding's inequality says that the deviation of R hat of M from its mean is not going to be too large, right? So Hoeffding's inequality is going to say that R hat of M Z minus T of pi H 0 Z, which is its expected value, is so with probability 1 minus delta. So for every Z in C, with probability 1 minus delta, this deviation is more than equal to the scale of the values that we're averaging, which is 1 over 1 minus gamma times the square root of 2 over delta divided by 2m. So if we want, and this is what we want indeed, we want not only this, but we want to control these errors for all values of Z in C simultaneously. We need to apply a union bound for that. So if we add a union bound for that, so that means that you just split the errors equally. So this delta error probability is split equally across all Z in C. Then you get that with probability 1 minus delta for every Z in C. So here it was like for every Z with probability 1 minus delta something holds. Here it is for with probability 1 minus delta for every Z the following holds. These deviations so here, as I said, the sort of the error, the failure probability is equally split. So you have to replace delta with delta over C. So that makes the coordinate of C appear inside the log. All right. So now, outside of this error event, and the error event has a small probability, we're controlling how big these deviations are. And so if we pull everything together, what we find is that with probability 1 minus delta, epsilon z, for every z, epsilon z is smaller than equal to this first term, plus what is the second term? So epsilon z is going to have first term, second term, and third term. The second term is going to be the truncation error, which is gamma to the power of h divided by 1 minus gamma. And the final term is going to be just the approximation error that we inherit because we are using features. So this holds for every z. Therefore, this maximum can be upper bounded by this value. And going back to the error of predicting q of pi, we see that the error of q of pi, predicting q of pi, is going to be this error that we just bounded, plus, so that's that, plus epsilon pi star. So another epsilon pi star appears. So we can phrase this as the following lemma. this probability 1 minus delta, it holds that the maximum error that we're going to see if you apply our procedure to make these predictions is going to be smaller than or equal to epsilon pi star plus square root d times epsilon pi star plus gamma to the power of h divided by 1 minus gamma plus this 1 over 1 minus gamma times the square root from here. So that's the same square root, which is just the same as this. I'm not going to copy those.
Is there a max here? A
There's
max
no max.
overhead when you apply
The
union
right-hand
bonds,
side? What?
the left-hand side, on top of the page.
Which top now or top earlier or like?
Right now.
On the top of the page, this was holding for a given z. Okay, so you have just 2 over delta. If you apply a union bond and you want to have an error event such that controlling the error for every z, not just for a single z, then you have the c appearing there. Right, so that's the price that you pay for controlling the errors for all elements of the set C. And now the really lucky thing, yeah, Hongming asked whether the rewards are in 0, 1. When we apply the truncation result, yes, that's the assumption. So we are very lucky because C is small. So notice that the quantity of C is d squared. So log C is just log d. So that's really nice. So here, on the right-hand side, nothing depends on the number of states. So we can control the errors everywhere. So the quantity of this big set doesn't appear on the right-hand side. If you want to make these errors small, there is going to be a floor to it. How small you can make this error. The smallest error that you can get is this, right? Because that was the approximation error. Like no one can approximate this function better than this approximation error. So we see that we're gonna pay a price because, okay, if I take h to be big, I can make this small. Here, I'm showing that there is this 2m, so divide by 2m. If I make m big, then I can make this small. So this can go to 0 as m goes to infinity, and it doesn't have to be too large. And this goes to 0 if h goes to infinity. And it doesn't have to be too large, right? So if you want to make the errors of the size of just the approximation error times, I don't know, 1 plus square root d times, I don't know, 3 or something like that, 3. then you can calculate, okay, how big should h be such that this is equal to the approximation error, or less than equal. How big should, so that says that h should be, you know, the effective horizon with this target, right? So that's just like 1 over 1 minus gamma and log 1 over epsilon approximation error. Similarly, you want to control this other term, the very last term, Okay, I'm going to write this back. So this was coordinate of C divided by delta over 2m, and you want to make it smaller than the approximation error, let's say. Then how big should m be? You solve it for m, and you see that, well, m should be, I don't know, larger than 1 over 1 minus gamma approximation error squared times log 2c over delta. Okay, so recall that this is just d squared, so this depends in a mild fashion on the dimension. And so if you use these many trajectories at these d squared states, then all the errors are going to be under control in every iteration. Okay. So this seems doable, but there is a little spoilage. The problem is that we wanted to run policy iteration, and now the way we are running policy iteration, every time we evaluate the policies, we introduce some error. Okay. So how are we going to do this? Like you start with a pi naught, and then you want to evaluate pi naught. Well, that normally would be calculating this, but that's too hard to calculate. So you're not going to calculate this, you're going to calculate some coefficient. And then use phi theta naught. That's going to be a guess at what the value function of pi naught would be. But there is a little approximation error here that arises. And we just elaborated how we're going to control it by choosing m big, choosing truncation horizon big. We can control that error, but it's not nothing. And then we can't do any better. Well, okay, so that's the first idea. Maybe we can do better, but what we can do is that we can choose pi 1 to be greedy with respect to q naught, not q pi naught. Okay, so q naught is not q pi naught. And then we can continue this. The question that we need to ask is whether this is a sensible thing to do. Are we still in control? Because we have all these errors that arise from approximately evaluating the policies, not exactly evaluating the policies. So we need to ask whether we can guarantee that this process is going to lead to some value functions, some policies whose values are large. So something times 1, right? So the suboptimality of these policies is in the question. And we want to know, okay, what so far, what we were doing is that we were controlling these errors. Is it sufficient to control these errors to conclude that the policy at the end is going to have a function that is uniformly large everywhere? The answer is yes. So things are not so bad as long as you can control the L infinity errors. So this question mark can be replaced with, I don't know, something like 2 times the maximum. Okay, I'm not going to go there. Like I rather derive what we can get, because whatever I write, I make a mistake. So that's the question. Like, okay, if we're controlling the errors, so somehow we're controlling the maximum of these, I don't know, I of all these errors in an infinity norm, like let's say all of these are small, then is it sufficient to conclude that for k large enough? So earlier we knew that if k is like, I don't know, the effective horizon, then we are already close to optimum. So how does that work now? So notice that you can abstract away all the details of how you're evaluating the policy. It doesn't matter. Like from the perspective of the analysis that comes, what matters is that we're controlling the errors. And we're just interested in like, okay, if we were able to control the errors, would that mean that policy iteration would still be an okay procedure? How sensitive is policy iteration to the errors? So sensitivity analysis of policy iteration. And the result is going to rely on a lemma, which you could say is the progress lemma that we know for policy iteration, but just for this approximate policy iteration. So API stands for approximate policy iteration. When you just write that, okay, I have a function, I have a policy pi, let's just say memory rest policy. And I have a function which is almost the same as q pi, but there is some error, epsilon. Okay. And then I choose this pi prime, which is greedy with respect to q. So what does it mean? It means that its policy evaluation operator, if it applied to q, is the same as what you would get if you apply the Bamon operator, so maximizing operator. Okay. So pi prime is greedy with respect to q. So this is just like a very complicated way of writing that m pi q is equal to mq, which you may still find complicated, but it's like just a handy shorthand for saying that pi prime selects actions at every state, which give you maximum values of this function over the state action values. This holds for every s. It's just a shorthand for that. And so, so you have this policy pi, you have this function q, you write it in this form, and you define pi prime as the greedy policy with respect to q. And the lemma states that q star, you're making progress. The distance between q star and the new policy, the action value function of the new policy, is not much more than gamma times the distance of the similar quantities, but just for the previous policy, plus, and there is some error. Okay. So this is what the progress lemma says. And this is very similar to what we had before for policy evaluation. What we had before is that this term, this epsilon term, which is 0. So when that term is 0, then this is just 0. And then you just have this progress, and you see that you're exponentially fast converging. So this was the lemma that we used, just with value functions, not action value functions, that we used when we were arguing about the convergence speed of policy iteration. We were saying that, oh, policy iteration converges at least as fast as it converges at the geometric rate. So I see some questions about this epsilon. So epsilon is the function from state action, the state action set to the reals. It's anything. It's just a function. Okay. So these are, remember, vectors or functions. And so if I write q is equal to q pi plus epsilon, then since q and q pi are functions, epsilon must be a function. Okay. All right. I'm going a little bit over time, but I really want to finish this. So how do we prove this? So maybe I will just leave out one step, but like the proof is very similar to what we have seen many times before. It starts by writing what we want to bound, or is known we want to bound, and let, okay, pi star be an optimal memberless policy, which we know exists. So, yeah. So we know that q star is a fixed point of the underlying policy evaluation operator of this policy. So we can write T of pi star q star in place of q star. And since we want to somehow bring in this term guy, this guy here, we're going to start to subtract and add, and we subtract the term that we would like to sort of appear. So we want to see the action value function of pi appearing. So we subtract that. So now we have to add it back. And so at one point we will need to use, and we will need to switch to pi prime. So to be able to do that, we need to somehow bring in q. And q is close to q pi. So every time you see q pi, you might think, oh yeah, like that's almost like q. So because of that, we're gonna just bring in q here. Okay. And that's really good because if you bring in q, then you can switch to pi prime, because pi prime is greedy with respect to q. So this means, okay, so that means that this holds, but t is the biggest operator that you could get. So for any other policy, especially for pi star, you get something smaller than equal to t applied to q. So the policy salvation operator of pi star applied to q cannot be as large as if you take the max. Okay, you get something smaller. Because of that, this is upper bounded by 0. So that must be not a positive term. And then you have this. And then every time you see pi, sorry, every time you see q, you think that, oh, that's like q of pi. And then we end up with this. Okay. So because of the inequality that's up there, and these operators, all of them are linear operators. And if you recall, like this t of pi was equal to r plus gamma p m pi applied to q, right? So if you have t of pi applied to some function and t of pi applied to some other function and take the difference between two, the rewards are going to cancel. The gamma is going to come out. And we abbreviated this just as p of pi. And so you are going to see gamma times p of pi, and then apply to one of the functions, applied to the other function, p of pi is just linear operator. So we can pull out the difference. So just algebra. This is this is just the first term. This guy is equal to this guy that's written here. Okay. So now I have gamma pi star and q pi minus q. So that's like a negative epsilon, so that's fine. Now I drop this term, and I have from this term the epsilon, and then gamma times pi prime q pi minus q pi prime. Okay. So this is equal to gamma times p of pi star applied to q star minus q pi plus gamma times p of pi prime minus p of pi star applied to epsilon plus p of pi prime q pi minus q pi prime. So if we also had an epsilon somehow here, so if we are able to upper bound this by something epsilon, then we will be very happy. Lo and behold, this can be done. So you can write q pi minus q pi prime as, I don't know, I minus gamma p of pi prime inverse. So recall that this is the fixed point of this T of pi prime operator. And as such, this is equal to E minus gamma P of pi prime, inverse applied to R. So I'm just going to use this. Okay. So now, this guy here. So what do we see? So first of all, Q pi is Q pi is Q minus epsilon. So plug this in. So call this 1. So then 1 is equal to I minus gamma P of pi prime Q minus epsilon minus R. So this is Q minus gamma P of pi prime of Q minus R. And we might recognize that, okay, like if I just add these two guys together, I get something nice. And then there is this term that only depends on epsilon, and we like the epsilons. So this is T of pi prime applied to Q, and this is just Q. And now recall that what do we have? Like we have Q is equal to Q pi plus epsilon. If you apply T of pi prime on both sides, you get T of pi prime Q, which is what we have here. That's why I like it. Is equal to T of pi prime of Q Q pi plus gamma of P of pi prime of epsilon. Because of the this operator, only this applies to epsilon because the rewards are folded in here. And now we know that T of pi prime, oh, sorry, T of pi, okay, we should have applied this to this pi. So T of pi prime applied to Q is at least as large as T of pi applied to Q, which from this equality is equal to that. So if you subtract the two sides, so you're subtracting something smaller, and you get something bigger. And P of pi Q pi is just Q pi, so that cancels the first term. So this whole term becomes I minus gamma P of pi and epsilon. So altogether, because of this little calculation here, this is upper bounded by I minus gamma P of pi epsilon minus this other epsilon. So the identities cancel each other, and you just get P of pi prime minus P of pi epsilon. Plug this in. into 1, and you get basically the statement. That's why I stop here. We write up the lecture notes, and you will see how this ends. But okay, so the point is that this is going to become, well, okay, I can just write here. This times epsilon are bounded by that. You plug this in here, and so the first term is upper bounded by an epsilon. The second term is upper bounded by an epsilon. The whole thing is upper bounded by epsilon. You do some more algebra, and then you can show that this factor of 2, like the inflation it's just a factor of 2 of the errors. You take max norm at the end, like both sides, and then that's it. All right, and we have seen this, how to use this inequality. So if you have an inequality like this, you can iterate it, and it shows that you're controlling the errors. We have seen this in the proof of when we were talking about the sparse look-ahead trees. The same inequality appeared, and we were just iterating through it. So we know that if the errors have the exponential decaying nature, so here, this is the main thing. The previous error is multiplied by a factor smaller than 1, plus the newer error arises, but altogether the errors cannot overwhelm this process. So if all the errors are small, then the error in this process stays small. Okay. And then what remains is to put everything together and state what we can have, which is going to be that, well, in every iteration, we're going to control the maximum errors. Therefore, at the end, if the number of iterations is high enough, the truncation length is high enough, the number of trajectories per core state that come from the Kiefer-Wolf Phase Theorem is high enough, but all of these are polynomially irrelevant quantities, then you can get an error which is roughly of the size of the approximation error times square root of d times some universal constant like 5. So that's it. So that's the first result that we have for some value function approximation schema. We see that it's a little bit lagging because of the reliance of the feature map being so nice that we have access to these core states. Because like without that, if someone just hands you some feature map, you might never get these core states unless the feature map has some really nice properties without looking at all the state action comparison, and that's just too much. But if this is the condition, then you can do it. The only thing is that the approximation error is going to be blown up by a factor of square root of d. So the next time we're going to talk about that, whether that can be avoided. All right. Questions. When we write q without pi or star, does it mean the q is just a function not derived by any implicit? That's correct. Yeah, when I just write q, it's just a function. Like, yeah, we came around of these functions because you're using this function approximation schemas, right? So you just bump into various functions. All right. Is there any are there any outstanding questions in the chat that I haven't answered? I think we're good. Okay. So if we're going over time a little bit again, so much to talk about. So how do you like